our new unit called EMR, or electromagnetic radiation. Electromagnetic radiation was not first observed or discovered by Maxwell, but first explained by this guy named James Clerk Maxwell in 1861, a Scottish guy. You didn't hear too many Scottish scientists, right? A lot of German scientists, English, American. You don't hear a lot of Scottish scientists. Anyways, James Clerk Maxwell, 1861, starts talking about light, right? Visible light and other types of electromagnetic radiation. And he comes up with this theory as to where EMR comes from and how it's produced and what it looks like, what the composition of it is. He says essentially this, that accelerating electric charges generate electromagnetic radiation. They generate electromagnetic radiation because they generate changing magnetic fields. And changing magnetic fields will generate changing electric fields. And because EMR consists of changing electric and magnetic fields, that's what you need to produce EMR. Accelerating charges. Now, careful. We learned about different fields that electric charges can cause in different scenarios. If we have an electric charge that is at rest, it will generate a gravitational field. If it's at rest, it will generate an electric field. Will it generate a magnetic field? No. If it's at rest, it does not generate a magnetic field. Therefore, it's not going to generate EMR. If the charged particle is moving at a constant speed, does it generate an electric field, a gravitational field? Yes, it has mass. So it generates a gravitational field. Does it generate an electric field? Yes, it generates an electric field. Does it generate a magnetic field? Yes. If it's traveling at a constant speed, it generates a magnetic field. But it does not generate EMR. It doesn't generate EMR because you need to have a changing electric and a changing magnetic field to have EMR. And a constant speed electric charge just generates a constant electric and a constant magnetic field. Now we have a charged particle that's accelerating. Does that generate a gravitational field? Yes, it has mass. Does it generate an electric field? Yes, it has charge. A magnetic field? Yes. Now, because the charged particle is accelerating, it's generating a changing electric and a changing magnetic field. And because those are the requirements for EMR, then an accelerating charged particle will also generate electromagnetic radiation, or EMR. Why do we need these changing electric and changing magnetic fields? Let me tell you a little bit about the composition of EMR to help you to understand why this changing thing that I have underlined and italicized there is so important. If I have an accelerating charged particle over here on the left side of the room, it's going back and forth, back and forth, back and forth. And as it goes back and forth, it has to speed up, slow down, stop, reverse direction, speed up, slow down, stop, reverse direction, and so on and so on and so on. So it's accelerating. It's accelerating this way, it's accelerating that way, it's accelerating this way, it's accelerating that way, and so on. That generates a changing electric field. And we'll see that changing electric field looks like this, kind of a sine wave. See that? I'm tracing it out with my finger here right now. So it generates an electric field that looks like this. It generates a magnetic field that looks like this. Notice the electric field and the magnetic field are both sine waves. They're both in phase with each other. In other words, when we have the crest of one, we have the crest of another. And they're both blank to each other. It's perpendicular to each other, right? This word appears again. We said it appears lots in the last unit. It did. It appears lots in this unit as well. So you've got this changing electric field, this electric field that changes, this magnetic field that changes, that's perpendicular to it, in phase with it. Now, this is the important part here. Electric field number one, magnetic field number one. Electric field number one will generate magnetic field number two. And magnetic field number one will generate electric field number two. Then electric field number two will generate magnetic field number three. Magnetic field number two will generate electric field number three, and so on and so on and so on. If you have just a charged particle that's moving over here, not accelerating, but just moving, it generates a constant electric and magnetic field. Great, you got both. but it doesn't generate anything else. It's not self-sustaining because an electric field doesn't generate a magnetic field. A magnetic field does not generate an electric field. A changing electric field generates a changing magnetic field. And a changing magnetic field generates a changing electric field. That's where you get this electromagnetic wave from, is the fact that one phase of it causes the next phase of it, which causes the next phase of it, and so on and so on and so on. Does that make a little bit of sense? Okay, the word changing is so important because if you don't have the changing electric and changing magnetic field, all you got is an electric field and a magnetic field right over here near the source, and that's it, done. You flip on the light, what happens? Nothing. It doesn't move from the light fixture to your eyes if there's not a changing electric and a changing magnetic field. It doesn't sustain itself and propagate towards you. So you're never going to observe it. So what is EMR? Well, we kind of just talked about that. It's energy that travels as a wave, and it doesn't require a medium. So in other words, it can travel through empty space. It travels through empty space all the time. The light that you see outside right now reflecting off of those rocks came from the sun 8 minutes ago. It's produced at the sun 8 minutes ago. Traveled at 1 billion kilometers per hour from the sun for 8 minutes and finally reached us. Most of that was empty space. A little bit of it was the Earth's atmosphere that it went through, but it traveled mostly through empty space. Just because the EMR can go through empty space doesn't mean it needs to. Clearly, it can go through air, it can go through water, it can go through glass, but it has the ability to go through empty space. It consists of a changing electric and a changing magnetic field that are perpendicular to each other and in phase with each other. The only way to get a changing electric and changing magnetic field is if the charged particles accelerate. If there's 3 words that you would remember, that you focused on, so that you could answer any question that really I could throw at you up until this point, it would be these 3 words. Accelerating. The reason we remember that is because accelerating charged particles generate changing electric and magnetic fields, which are perpendicular to each other and perpendicular to the direction of motion of the wave. So honestly, you remember those 3 words, you're probably going to be able to fill in the blanks of any question that gets thrown at you. Accelerating charged particles generate changing electric and changing magnetic fields, which are required to have an electromagnetic wave, and those changing electric and changing magnetic fields are perpendicular to each other and perpendicular to the motion of the particle. Of the EMR, I should say. So they're perpendicular to each other, but also perpendicular to the way that it moves. So for instance, look up here, look at my hands here, my arms here. Let's say this is the electric field, this one's the magnetic field. Which way is the particle going to move? Sorry, which way is the EMR going to move? This way, or this way. Okay, one's on the x-axis, one's on the y-axis, going to travel along the z-axis. Okay, what about this? Electric field, magnetic field. Which way is it going to move? This way or this way, perpendicular to both of those waves. What about if I have it like this? Okay, at some kind of funny angle like this. Which way is it going to move? Either this way or this way. Perpendicular to each other, but also perpendicular to the direction of propagation of the EMR. Okay. There's a diagram. You can copy this down or not. If you understand what I've been saying, this diagram just graphically summarizes it, right? You can see that I have 3 axes here. I have an x-axis, I have a y-axis, and I have a z-axis. You can see in this particular one, my electric field is on the y-axis, my magnetic field is on the z-axis. They're perpendicular to each other, in phase with each other. When you have a crest of one, you have a crest of another. And which way are they going? Along the x-axis. So I had z and y for my fields, travels along the x-axis, perpendicular to each other, perpendicular to the direction of motion. You can see that it's a sine wave as well. Right here would be my source, my accelerating charge, which generates this changing electric field and this changing magnetic field. Okay, this changing electric field generates this changing magnetic field. And this changing magnetic field generates this changing electric field, and so on and so on. Now, we already think of EMR as a wave, right? We said that Maxwell's theory was that it's energy that travels in a wave-like form caused by an accelerating charged particle, produces a changing electric, changing magnetic field that travels perpendicular to both of those fields. Can we prove it? Well, there's evidence to support the wave nature of EMR. For hundreds of years, there's been debate about whether light is a particle or a wave. Newton thought light was a particle. Maxwell thought light was a wave. Well, there's 4 pieces of evidence to support Maxwell's wave theory of EMR, that EMR is, in fact, a wave. EMR undergoes diffraction. Diffraction is a property of waves, but yet EMR exhibits diffraction, so therefore EMR must be a wave. Do you guys remember what diffraction is? You learned about it briefly in Physics 20. Yeah, kind of. Yeah, it spreads out. As it goes through the gap, it spreads out. So here's a wave, goes through the gap right there, and as it goes through the gap, it spreads out like this. That's a property of waves. If you have water going through an opening like that, the water is going to diffract and spread out. If you have sound going through an opening like that, the sound is going to spread out or diffract. If you have EMR, any kind of EMR, including visible light or including radio waves going through a gap like that, it's going to spread out. So EMR undergoes diffraction. Diffraction is a property of waves. It's exhibited by EMR, so according to that, EMR must be a wave. Interference is another one. Remember in Physics 20 interference? If you had a wave that looks like this and another wave that looks like this, then they would combine to form a wave that looks like this. That's called constructive interference versus destructive interference, where you produce a smaller wave. Remember that? Interference is a property of waves, but it's exhibited by EMR. If you have 2 beams of light and they intersect with each other, crest intersects with crest, then you end up getting a brighter light. Yeah? Yes. Yeah. If it's out of phase, yes. Probably. Probably. I'm not sure exactly what, but probably. Another property of waves that's exhibited by EMR is called refraction. We would have briefly mentioned this last year. Just briefly, though. We were talking about waves and boundaries last year. We would have mentioned the word, but no, not in any kind of detail, because it's not really required in Physics 20. If here's a boundary, and you have a wave going towards the boundary like this, it strikes the boundary, and as it does that, it changes speed. Either speeds up or slows down. And as it does that, it also changes direction. When a wave goes from one medium to another, it changes direction. It refracts. So does EMR. Since refraction is a property of waves, and EMR exhibits refraction, then EMR, according to this, must be a wave. The last one we have, it's called polarization. Probably don't know what that is. You might have heard of it before. You have polarized sunglasses. Polarized sunglasses cut down on the glare. Good sunglasses tend to be polarized sunglasses. Polarization is the filtering out of certain components of waves. So if you have let's say you have a horizontally polarized wave, it filters out everything but the horizontal wave. Let's give you an analogy here. I got a piece of plywood. And in that piece of plywood is cut this rectangular slit, this rectangular opening in this piece of plywood. I got a string passing through this plywood, or a rope passing through this plywood. Jaden's on one side, Mason's on the other side. Okay, one guy is holding onto one end of the rope, one guy is holding onto the other end of the rope. Mason gives it a flick like this, vertically like this. He produces a sine wave in that rope like this, right? That wave goes right through that opening. As long as the rope is going through the opening, the wave carries through that opening. But what if Mason does this? What if he flicks the rope like this, sideways? how much of that horizontal wave that looks like this makes it through that vertical opening? None. What if you did it at an angle like this? How much of it would make it through that opening now? Some of it, the y component of it would make it through that opening, right? We say that we've polarized that rope wave vertically. We're allowing only the vertical component of that wave to make it through. Now, on the other hand, we could have another piece of plywood that looked like this, with a horizontal slit or a horizontal opening there. This time when Mason makes this vertical wave, how much of it makes it through? None. He does this horizontal wave, how much of it makes it through? All of it. He does his angled wave, how much of it makes it through? The horizontal component of that wave. So we'd say in this case it's polarized horizontally. I got some polarizing filters right here I'm going to have you take a look at. We'll hand out a couple to each, to kind of make some small groups and hand out a couple to each group. What I want you to do is, with these, is a couple things. Firstly, take the first one, look at the light. You should be able to see the light right through it, easily. Second one, you should be able to see the light right through it. Then I want you to put them together. I want you to put them together and look at the light. You should be able to see the light right through it. It might be a little bit darker, but you should still be able to clearly see the light right through it. But watch this. Mason's going to be able to see this right now. Mason, can you see me?
Yeah.
Okay. As I turn this 90 degrees, what happens? I completely disappear. Okay. This is let's say this is a polarizing filter that filters it in one dimension. This filters it in another dimension. Okay. It's like this. If I have this one and look at the light, I can see it, although it's vertically polarized. I have this one. I look at it, I can see it, it's just horizontally polarized. But if I put them both together such that one is horizontal and one is vertical, the front one filters out everything but the vertical, the back one filters out everything but the horizontal. What are we left with? Nothing. Nothing. EMR, visible light, exhibits polarization. And polarization is a property of waves. Therefore, EMR must be a wave. Let's do this one. This will be our last slide of the day. This is just going to describe for us the different types of EMR. We already know the 7 types of EMR, right? Ranked in terms of increasing frequency. What was the first one again? Radio waves. What was the second one? Microwaves. Good. You guys are remembering this from the song. What's the third one? Infrared. Yeah. What was the fourth one? Visible light. Now pause for a second here because I want to go into a little bit more detail with visible light. There's 7 types of visible light as well, 7 bands of visible light. There's bands of all of these types of EMR, right? UV, we have UVA, UVB, UVC. We have different colors or different bands of each of these. But the most common ones, the ones that we're most familiar with, are the ones that are with invisible light. What are the different colors or the different bands with invisible light? Yeah, you learned this in elementary school, right? Red, orange, yellow, green, blue, indigo, and violet. Roy G. Biv. What do you think the word infra means? What do you think the word infra means? Before. Infrared. Before red. What's the next one that comes after violet? Ultraviolet. Ultraviolet. Yeah? Sorry.
Testing the temperatures of the different visible light.
What's next? What sounds bigger than ultraviolet? What sounds meaner than ultraviolet? X-rays. X-rays. And the last one is, of course, going to be gamma rays. Now, I've got these color-coded for a reason. Radio waves and microwaves are both produced in a real similar way. It's all accelerating charged particles of one type or another, but we have them color-coded according to specific mechanisms by which they're produced. Radio waves and microwaves are both produced by oscillating electric charge. And what that means is that the electric charge is going back and forth, back and forth, back and forth. The electric charge in the walls of your house is going back and forth. It's AC current, alternating current. Electrons are going back and forth at 60 cycles per second. It actually generates very, very, very low intensity very low frequency radio waves. Small enough that you're probably not going to measure them normally, but they're there. Sometimes you drive under a power line in a highway listening to a hockey game on a radio or something like that, and all of a sudden it cuts out because of interference with the radio waves that were generated by the power line above you. The frequency is right. Oscillating electric charge going back and forth, back and forth. Some of you might know the answer to the next one, the yellow ones here. How are these guys produced? If you've taken chemistry class, you might have learned this. These are produced by transitions of electrons. Transitions of electrons from a high level to a low level. In atoms. An electron makes a transition from level 3 to level 1. A certain frequency of EMR is given off. It makes a transition from level 3 to level 2. A different frequency of EMR is given off. It makes a transition from 3 to 2 in a different atom. A different frequency of EMR is given off. Generally, we say these three types of EMR are all produced by transitions of electrons, just different transitions, that's all. Different transitions, different atoms. X-rays are produced, go to the doctor, get an X-ray, go to the dentist, get an X-ray. Ever bother you? Used to bother me when I was younger, didn't know anything about it. Go to the dentist. The dental hygienist would put those things in your mouth, put the X-ray machine up against your side of your face, and then say, like, everything good? You comfortable? And you say, yeah. And then he or she would, like, take off running, hide behind a wall. Ever bother you that it's like, wait a second, if this is safe for me, why does she have to run off, hide behind a wall? Because I get one of them every year. She gets 100 of them every day. Okay? X-rays do damage to your body. They do damage to healthy cells every single time. As soon as you get an X-ray, you're doing damage to healthy cells every time. But generally, our body's pretty good at repairing itself. So if your body can repair itself quicker than the X-rays do damage, you're fine. You're going to be fine. But if the X-rays are doing damage quicker than your body can repair itself, then you're not fine. Then we have all kinds of possible complications, including things like cancers that form. X-rays are produced in dentist's office and doctor's offices, hospitals, by rapidly decelerating electrons. We get electrons going to crazy high speeds. It's called an X-ray tube. Accelerate them across the potential difference to insane speeds, like 10 to the 7 meters per second. Like approaching the speed of light. And then we smash them into this target, and they stop almost instantly. They had a lot of kinetic energy. That energy has to go somewhere. A massive amount of kinetic energy has to get transformed into a high energy type of EMR, like an X-ray. So this photon of X-ray ends up getting released as a result of that. Gamma rays are produced by nuclear decay. I should have made these two different colors. Nuclear decay, which really boils down to matter being converted to energy. We'll talk more about all three of these in a lot more detail in our next unit. But for now, just remember that matter can change into energy. Einstein said that, right? Equals mc squared. Einstein said that matter can be converted to energy. And as it is, gamma rays are given off.
What is that M? Or what is this?
C is the speed of light. 3 times 10 to the 8. Now, we are responsible for every frequency, every wavelength, and every energy. If I'm given a question that says the frequency of a particular photon of EMR is 5.0 times 10 to the 14 hertz, you have to be able to tell me what type of EMR that is. If you're given a wavelength of 6.0 times 10 to the negative 8 meters, you have to be able to tell me what type of EMR that is. If you're given an energy of 3 times 10 to the negative 19 joules, you have to be able to tell me what type of EMR that is. That sounds difficult. But the good news is, all we got to do is remember 3 different frequency ranges. We can figure out the rest. I want you to remember, you need to remember, the frequency range of microwaves is 10 to the 9 to 10 to the 12 hertz. Memorize that number. You have no other way around this. You need to memorize that number. Visible light, we get a little bit more specific with visible light because visible light is a smaller range. It's a much, much narrower range. It's 4 times 10 to the positive 14 to 7.5 times 10 to the 14 hertz. So we're not just giving you an order of magnitude for visible light, we're giving you a base as well, 4 to 7.5. And X-rays, well, they're 10 to the 17 to 10 to the 20 hertz. 10 to the 17, what about in between? That's a good question. Yeah, that's why I'm telling you, all you need to do is remember those 3, right? Because if you're given a frequency that is, let's say 5 times 10 to the 14, you know that's visible light. 5 times 10 to the 19, you know that's X-rays. What if you're given 5 times 10 to the 16? It must be UV. It's got to be UV because it's in between. What about 5 times 10 to the 23? Got to be gamma. What about 5 times 10 to the 7? Got to be radio waves. 5 times 10 to the 10? Got to be microwaves. So memorize these 3. If it falls somewhere in the range of these 3, great, got it. If it falls somewhere in between one of these 3, or 2 of these 3, figure it out. Just fill in the blanks. Notice the frequency is increasing. Radio waves have the lowest frequency, gamma rays have the highest frequency. Let's do wavelength now. What if you're given a wavelength of, let's say you're given a wavelength of 6.0 times 10 to the negative 8 meters. 6.0 times 10 to the negative 8 meters. What's that? Well, we didn't memorize any wavelengths, right? Here's what I want you to do. Find the frequency using the equation that you learned in Physics 20 called the universal wave equation. V is equal to F times lambda. Remember that? The speed of light in a vacuum, the speed of any kind of EMR in a vacuum is 3 times 10 to the 8. Lambda here would be 6 times 10 to the negative 8. That would give me 5.0 times 10 to the... Wait, I just solved for frequency. Now I can compare it against the 3 ranges that I memorized, right? 5 times 10 to the 15, well, that's going to be ultraviolet because it's not visible light and it's not X-rays. It's got to be ultraviolet. So 21 different ranges, 7 frequencies, 7 wavelengths, 7 energies. Memorize 3 frequencies. And then if you don't get one of those 3 frequencies, then figure it out. It's in between. If you get a wavelength, then find the frequency and compare it against your known frequencies. You can do something pretty similar with energy. There's an equation that relates energy to frequency as well. I'm just not going to tell you what it is yet. That's going to come a little bit later on in the unit. For now, you're going to have to just trust me that at some point later on in the unit, sometime after Easter break, you guys are going to be able to figure out what type of EMR you have based on the energy in a similar way as which we just did that.